co-chairs for SHIMA's Professional Development Committee, and I am so happy to be able to introduce this lovely panel and webinar on collaborative field studies of air quality in dental school laboratories. And now I will turn it over to our speakers. Time at the end, they are open to discussion, but please post in the chat or the Q&A. I'll be watching it for them. All right, thank you. Turn over to Christy.
All right, well, thank you so much and welcome to our webinar. We're really glad that you could join us today. I think what I'll do now is go ahead and turn off the camera so that we can focus on the content of the presentation, and then we'll turn cameras back on when it's time for discussion. So let me do that. And here we go. All right, so in this session and the work that we're going to discuss today really came about from our presentation at SHIMA in 2023 when we were presenting our guidance document on 3D printing, and we had co-created that with SHIMA. And during that session, we had some collaborative discussions around issues people were facing on their campuses related to 3D printing. And so several people brought up that day the proliferation of 3D printing in their dental schools as an emerging topic. And so since that time, we've worked with our friends at Nova Southeastern and Texas A&M to do some field studies on the air quality in dental schools. And so I'm telling you all that because I just really like how this represents this great full circle moment for us. We did some research that led to creating a partnership and then a guidance document with SHIMA, and that then led to more research in an area of emerging concern. And I just think it's been a great partnership and really appreciate the opportunity to work together. But one of the things that I really do love about doing this work together is that we did this work together and we have such a great group here today. So I'm Christy from Chemical Insights Research Institute. We like to call ourselves CIRI. We have Decca from Texas A&M. We have Beth from Nova Southeastern University. We have Mark from CIRI, and we also have Chen from CIRI. Next slide. And here are the learning objectives for the time together today. I'll just give you a minute to read those over. All right. Next slide. And really the way that we'll achieve these objectives, it's here in our agenda. So I'm going to first just give you a brief introduction to CIRI and what we do, and how that has led to our partnership with SHIMA and our collaborations with SHIMA members at these institutions as well. And then I'll do a high-level overview of just the different types of 3D printing and general hazards associated with each of those. That'll be just very quick. And then I'll turn it over to Beth and Decca, who are going to give you an overview of the facilities that we studied and some of the issues that they faced there. Then Mark and Chen will talk about what we found from the field studies that we've done at those locations. And so, like Elizabeth said, we do want to leave some time for discussion at the end if we can as well. So next slide. And actually, we can go on to the next one. I just wanted to start with a brief introduction to our organization. We are Chemical Insights, or CIRI, and we're a research institute of UL Research Institutes. So we're part of that larger Underwriters Laboratories organization. And as part of UL Research Institutes, though, we are a 501c3 nonprofit. And so we're focused on research and public safety. Next slide. And at CIRI, we're dedicated to scientific research, publication, education, and communication on environmental exposures that typically result from technologies and practices of our kind of modern world. And we characterize those exposures, but then we also look at their impacts on human health and ways for reducing the risks. Next slide. And we have research initiatives that span really a number of topics, but they're all related by this idea of environmental exposures that result from technologies and practices. Like I said, also looking at their impacts on human health, we have a very advanced toxicology lab, and we look at ways for reducing the risks. And a lot of people around SHIMA, if you could click, Elizabeth, know us, thanks, as the 3D printing people, because we've done a lot of work in that area, but we are researching exposures and health impacts in a variety of other areas as well, as you can see. So happy to discuss any of those other areas. You know, if you want to reach out to us directly or after, after the webinar, we'd be glad to discuss any of these other topics as well. But next slide. I do want to show you kind of our way of working. We just talk a lot about research to impact, and we've turned this into a proven process that allows us to deliver meaningful insights for real world applications with all of our research initiatives. So of course we start with the research, we identify knowledge gaps and we do the scientific research. That's kind of the heart of what we do. But we publish in peer-reviewed journals. I mean, we do want to be seen as thought leaders in our areas, but we don't stop there. And I think that's the important thing to note, and that's what makes the difference, is that it's important to us that our research results be accessible and understandable and actionable. So we try to maximize our impact. We translate those findings and try to create resources, or actually in a variety of ways, we try to reach different kinds of stakeholders. So we might create standards that can be used to certify safe products, or we might create educational tools like the guidance document that we created with Shima, to get the resources to people who can put the recommendations from the research into action. And we also partner with organizations like Shima so that we can kind of extend our reach. These kinds of organizations can help us get our resources out there to stakeholders and really make more of an impact. So next slide. I wanted to show you that, and also to bring home the point that these partnerships are really essential to us and to what we do. We had originally partnered with Shima as what we might call an impact partner, a partner organization that helps us get resources into the right hands. But now that great partnership has led us to form new relationships at institutions of higher learning and given us the opportunity to do some additional research in the form of these field studies. So again, I just really like that full circle moment that we've experienced. So next slide. So now I'm just going to do a brief overview, I guess, of 3D printing technologies and some of the hazards. Let's go next slide. Most of you probably know that the basic idea of 3D printing is that it is a form of additive manufacturing. And so additive manufacturing methods, they build objects by adding material layer by layer. While subtractive manufacturing, in contrast, and these are more traditional, they remove materials to create parts. And so additive manufacturing typically results in less waste. And there are different ways to do additive manufacturing. And we often talk about the big 7 that I've listed here. There's really 7 main types of 3D printing technologies, and there are new ones being developed kind of as we speak. For example, bioprinting. We have a bioprinter in our toxicology lab, but I didn't include some of those newer technologies here because we often do talk about these big 7. Next slide. And I won't go over all of this, but I wanted to present it to you. And it is found in our guidance document that we've published with Shima, or you feel free to take a picture if it's something that you think might be useful to you. But I wanted to point out that the general hazards that are associated with 3D printing are always related to the specific process and materials that are used in that process. So the particular hazards can really vary a great deal based on the technology that's being used. Next slide. And in this particular presentation, we're going to zero in on vat photopolymerization. And that's because in dental schools, the most common 3D printing technology that's used is vat photopolymerization. And you might hear it called stereolithography, digital light processing, other terms like that. But the idea is that a liquid photopolymer is selectively cured by a laser source. And this is very common in dental schools because you can create high resolution, finely detailed parts with this kind of technology. But some of the hazards can include inhalation exposures to VOCs, dermal exposures to the resins and the solvents that are used. There's potential for UV exposure, and you're dealing with flammable chemicals. Next slide. And there are basically 3 steps in the process. The actual printing is where the laser source is selectively curing the resin to make the part. Then there's the wash stage where excess resin is removed from the finished part, and that's typically done with an alcohol rinse. And then there is an additional post-curing stage with additional UV light. Next slide. And we've characterized the emissions from this type of 3D printing in our exposure chambers in our labs in Marietta, Georgia. And based on that research, we've seen that both the printing and the post-processing stages showed very limited particle emissions, but high levels of VOC emissions. And that makes sense because of how the process works, right? So minimal particle emissions, but we did see elevated VOC levels even before the printing process started. And that's because the vat is sitting there with the resin already loaded into it. And then we also saw continuous off-gassing after the printing process had been completed. Now, all of this is interesting, but these are laboratory studies, done in our exposure chambers. So we've extended the work by partnering with Nova Southeastern and Texas A&M and doing some field study measurements. And so now I want to turn it over to Beth and Decca, and they're going to talk about the specific facilities that we studied and some of the issues that they faced there.
Thank you so much, Christy. You can go ahead and advance to the next slide for us. So what we noticed, and what, as Christy mentioned, what started the evolution of where we are today is an explosion, if you will, of 3D printing, especially in at least my program in the dentistry area. This technology is expanding overnight, and we're seeing the applications growing quite significantly. And as a result of that, we wanted to really dive into this a little bit further. So let's proceed. So I don't know if you have a dental school or not, so we're going to give you a little insight to what it looks like at a dental program. However, I hope what you take away from our presentation is that the applications for 3D printing are certainly far and beyond just a dental program. But this is an example of one of many 3D printers we have at our school. So proceed to the next slide and I'll show you some more information here. So the possibilities truly are endless. We are seeing it significantly in dentistry, and it's even becoming in-house. When you go to your own personal dentist, it is very likely now that they have their own 3D printer on property. So in the case of a professional facility like a dental school, you're going to see more of them. But even in our home dental offices, 3D printing is becoming a reality. The possibilities are endless, and that's why they're so desirable. We're seeing them continuously involved in personalized healthcare. There's improved efficiency on how they're operated, so the return on investment is quite valuable to the end user. And it's also been able to offer more enhanced treatment options for the patients. So it's certainly quite significant. But again, I want to emphasize the possibilities go way beyond dentistry. So what's the way beyond? Already in our program, we're seeing collaboration with our audiology department. And I expect we're going to see even more of this. So depending on the 3D printer, there are open systems, which means that it can basically print and be programmed to do whatever you need it to do. So some 3D printers are closed systems, think more like Apple phone versus a Samsung phone where it's an open system. And so because of that, our program has started to stay away from the closed system 3D printers because they are welcoming and leaning into the cross-college collaborations and printing now well outside of the College of Dental Medicine. What are the benefits? I think the benefits are pretty obvious to everyone. The precision and accuracy from early 3D printers has evolved significantly. It's also more cost effective. We used to send out all of these models to be manufactured for us, and now we're able to do it in-house, and it's pretty easy to do it. So it offers us the ability to be more patient-centered and offer more personalized assistance to the patients. So it's really highly, highly beneficial. And then being able to take an impression or take essentially pictures now in the morning and be able to fit somebody in the afternoon or evening is really incredible with the turnaround time ability of a 3D printer. And truly, the innovation is, we're just scratching the surface when it comes to innovation. New materials are constantly evolving along with the new applications. So with everything that's great, sometimes there's another side of that coin. There are some of the drawbacks. And so depending on the 3D printer, the initial cost can be quite significant. We have some that have cost upwards of $10,000. And then the material can be limiting depending on what it is you're trying to achieve. However, we're noticing that that's one of the challenges we have, is that the materials are quickly evolving. Along with the evolution of materials, so are the hazards evolving. And then, of course, you've got processing complications, which results in exposures that we as health and safety professionals are definitely concerned about. Then we start questioning things like, well, what about the sterilization? Well, what are the industry standards? And we quickly realize there really are very few regulatory standards associated with this. And then the learning curve is there as far as how to utilize this equipment, but even that is becoming easier and easier as the equipment keeps pace with technology. The printing time can be a little slow, so we do see some backlog, but they're, of course, just like everything else, improving that as well. There is some size limitations depending on the equipment you pick. However, for the most part, it's meeting all the needs of our program, only maybe they want higher throughput. And then there's different technology issues as it would with any operation of machinery. We're starting to question, what about intellectual property concerns? Are there any legal design issues that we're going to encounter as we do research with these materials? And of course, there's that regulatory hurdle. As an EHS professional, I'm continuously worrying and being concerned about any regulatory obstacles that we're faced with. These are certainly complex, they're not straightforward. And then there may be some quality control issues with regard to 3D printing as well. And I'm going to pass it over now to Decca, and we will circle back with you all again shortly.
Thank you, Beth. So we looked at ours from a perspective of starting off a new lab, simply because for me, it was like I got hired on and here you go, 3D printing lab. So basically, if you're starting off a 3D printing lab, this is some of the things you might experience or some things you might want to look out for. Now, like vet school, they produce a lot. Ours is a little bit more based off of like patient care, right? We get the patients in and basically do their 3D printed based off of what they need treatment for. So with that being said, our disposal level for the resin kind of like peaks depending on when we have a lot of patients. Oh, we have patients who need care that requires prosthetics. So with that, we had to figure out exactly how to work our disposal. So what we ended up doing, or what we came up with, was to see if we could dry out the resin, right? Disposal is a big issue. So we figured it'd be better to make it more solid waste. So essentially, we take the resin once it's done, we dry it out, let it become solid waste, and dispose of it that way. So biggest thing to remember is, if you're going to deal with waste, you might have to figure out exactly what works best for your campus and how to go about disposing of it. The second one is the smell that usually comes from it. It is a very strong smell, right? So for most people, I want to say most of our clinicians who work in that space are already used to it. So they don't quite mind the smell, but at the same time, there are people who don't quite feel comfortable with it. So we figured out PPE was going to be a big thing, and we made sure like we provided the right PPE and sort of like encourage people to use it. Essentially, with dental practices, you already have people wearing like masks, so that's like a regular thing. But in that space, they don't quite need to, except if they don't like the smell. So it's not a hard push, but it's like, hey, if you're going to be in this space, make sure you take account of PPE and make sure you have it. So next slide, please. So the other part is from what we've seen, most of the issues that could come with this is a little bit more chronic. So you're not going to have people experiencing issues right out, right? And two things that we noticed was staining is a part of the process. It's not directly part of 3D printing itself, but it's the next thing after 3D printing, because once the product is printed out, it looks a little bit like what you would use in the costume. So the clinicians, the technicians have to go in and stain it to look a little bit more like what the patients could use. So, but with that though, you have the issue of the smell coming off of like the staining material. So we figured with that one, basically exposure is one of the big issues you have to be concerned about if you're going to have a 3D lab, right? So we looked at exposure in two different aspects. One, the aspect of it coming from the staining material. So we figured, okay, if you're going to be in there doing your staining, maybe you take a little bit of a break, right? You stain for a little bit, you leave, you come back in. That is more streamlined simply because it goes into the smell of the resin as well. So we figured, okay, we're going to have this one benchmark that if you're doing staining or you're going to be exposed to the resin, since the 3D printing itself takes about 45 minutes, you don't have to sit in there for the whole 45 minutes. Just pop in, come back out. That way you're not exposed to any of the things that we don't really want you to be exposed to for a long period of time. So if you're going to do 3D printing as a lab, just be cognizant of exposure levels and maybe work out what you want to do as an administrative control. Next slide, please. The other one we noticed was alcohol is like a big, it's almost, at least from my perspective, so it's almost difficult to work this whole process without having that. So what we noticed was we had to make provision for where alcohol was being stored. Now, from an EHS perspective, you have the issue of this being a flammable material, right? So just making sure you know you're going to have like flammable materials in there, which kind of led us to think, okay, from now on, whatever we do that has to do with 3D printing, we want to make sure there are flammable cabinets next to the spaces. But it's also the proximity of it, because you also don't want to build a space where your flammable cabinet is like way off and the clinicians have to go as far to bring it or something like that. So we decided we're going to set it up right next to the 3D printers. So that way it's easier for them to grab it, but at the same time, it's in an enclosed space, so it's not a source of fire or it's not a source of, or it doesn't like lead to something like that. The other big one was ventilation. So the way our space was built out, it's kind of like a smaller space. Bet's is like really big. Ours is a little bit smaller, and we house about like 5 to 6 3D printers in there, and they're constantly running. So when they're all running at the same time, ventilation becomes a little bit of an issue. So even though the space was built for it, with the number of 3D printers like exploding instead of, we figured it'd be better to just take account of that. So we're looking to see, we actually, Chrissy just sent us like the formalized document of everything. So we're looking to see if we could expand the space or maybe do a little bit more for ventilation, especially because we're assuming that 3D printer is going to keep getting bigger and we might have to fit in more 3D printers in there. So basically just make sure you prepare for like alcohol storage depending on how many 3D printers you're going to have, and also make provisions for better ventilation depending on what you intend to have in the space. Next slide, please. The final one is training. Basically, I learned the process while we were doing all of this. So we're basically building training models consistently. For now, the training models that we have fits what we have in this space. But with the research coming out, we're looking to do more training for anyone coming in, even for the people who've been there from the start, letting them know, hey, this is what we have on board now. This is what we found out. So we're going to have to change how we do things just a little bit. So if you're going to have 3D printing in your space, just remember, like, your training process is not set in stone. It's constantly changing. And with CIRI doing more research, it's better to incorporate it on a real-time basis than depending on a particular training model that worked when the space started, because you might have other things coming in, and with the developments going on, you don't actually know if what you used at the start is still going to work moving forward. So yeah. Oh, back to Beth, sorry.
Sorry, I had to unmute. So that was excellent. Thank you. And as Decca mentioned, there is a little difference between our two sites in that at the time I gave this presentation in Tampa, we had 9 printers. By the time I was back to campus, we now had 10. And we have a second dental school on both sides of the coast of Florida. And the other coast also now has 3 printers. So we just keep growing and growing. And I think that's, I don't know that if any of you can commiserate with me about this, but This is part of the challenge that we face sometimes in higher education, right? It seems like every time I turn around, they've, added another printer, and we were supposed to be having a stopgap through purchasing, but apparently that's fallen through the cracks. Anyway, so we continue to grow, and our operation runs all day long. They are extremely busy, and they're constantly producing both patient-specific product as well as products for education. So it's very challenging. And then in addition to that, some of our challenges are anticipating the research needs because they're constantly exploring and going into other areas. What's on the horizon potentially is even bioprinting. They're talking about that next. And then, of course, as I mentioned, touched on the other cross-college applications. So we had a space that was not ideal, and it was not ideal due to the ventilation. So I know that that question's been asked, what is the ventilation you have, right? So we were in a lab that was designed to be a lab. However, we quickly were able to determine that the ventilation design for that space was not keeping up with the overwhelming number of 3D printers they kept adding to the space. We have since relocated our lab into another space, but still, these spaces were not built out or designed specifically for this purpose. So it's a constant challenge that we're facing. I will tell you the initial response from the college was standalone filtration. That does not work. And I think as EHS professionals, you all can understand why I'm frustrated with, that is their sort of stopgap measure. It's really just not suitable for the type of exposures we're experiencing in these spaces. And the resins that we are handling, working with, and utilizing in these tools come from around the globe. The safety data sheets are complex. They have challenging information and a lot of concerning information that has us constantly studying how we're best going to protect the employees and the individuals working in this space. And there's very little regulation or guidance around us. So if we can move to the next slide. So as I mentioned, moving the slide was one of our next steps, and that has now been accomplished. And with that, I've been able to do some sampling. We have a continuous monitoring device now in that space that all of the individuals working in that space have access to this on their phones. So when they're running different pieces of equipment or running different processes, they can see immediately what kind of exposures they're getting, either to VOCs, formaldehyde, whatever it might be. I have really worked hard at strengthening our relationship with the College of Dental Medicine. We're working in lockstep on designing spaces for future use so that we can enhance the ventilation, along with our design and construction folks who, they just get called in to do a space and they just move forward with what they understand to be the design and intended use of a space without maybe always working with us as far as the subject matter experts for this ventilation concern. So next. Here are some screenshots that I took. These are screenshots of my phone showing you sort of what this device looks like. I'm not endorsing this product. I just want to make that really clear, but it has been helpful for our teams to get a quick snapshot of what is happening. How accurate is it? I really couldn't tell you. I would use it more as sort of a guidance, but we are finding it has really been helpful for those that are in that space, because I don't want them occupying the room, staying around these 3D printers when they're being utilized, especially if they start seeing that the ventilation is indicating that it's going yellow or alerting them more concerns of even going red. So, and then I'll just add that we just appreciate being able to collaborate with CIRI, and I'm ensuring that everything we're doing is going to protect the users of the space and those occupying the labs around us.
Yeah, I agree with Beth. Having Siri on board has really, me personally, has taught me a lot, but also like it's provided a different perspective for us as to how we go about this. So we still have about 4 3D printers. We have a 5th one, but we don't technically use that one all the time. They're located in a prosthodontics lab, and specifically for patient use. So it's only when we have patients who need it that we get to use it. So the clinicians then do the 3D model before they print it out. So, and it's specifically for the clinic now. Research is looking to incorporate it into theirs a little bit more. We just spoke about it, and hopefully in the future we could maybe expand to the point where we could print our own products in-house, where it's not just for clinic use. Next one, please. So this is what we're looking at, what's next for TAMU when it comes to 3D printing. So research is going to get theirs, and whatever training models we come up with for the clinic, it might be slightly different for research, but the base is still going to be the same, limited exposure levels, making sure the room is suited for 3D printing, and then also making sure that anyone who walks into that lab knows the right PPE to use. And then maybe if we can get one of the monitoring devices that Med School has as well. And yeah, that's basically it. And then we're still going to keep working with CIRI. I'm going to keep bugging Chrissy to see if we could get more ideas on how we could improve our systems moving forward. Thank you.
Thanks, Decca. And now I'm gonna talk about the field study finding. Again, about the background and the motivation of the field study is because now that we know the resin type 3D printing has been used in the dental school routinely, and also it could be a source of potential hazardous emissions. So our objective of the field study is to measure the indoor air quality in the dental schools and look at the impact of resin 3D printing on the indoor air quality. And the next slide shows our instrumentation about doing the field sampling. So one of the air pollutions we are interested in is volatile organic compound, or VOCs. Basically, they are just carbon-based chemicals that has a high vapor pressure in room temperature. And depend on the chemical composition of the VOCs, they can be irritating or toxic or even causing cancer. So we have brought our capability of our sampling techniques to the dental schools. On the left picture shows the VOC sampling. So we collect VOC air samples onto the 10x tube, shown on the left top corner. And after we collect the 10x tube samples, we take them into our lab and use the TDGC mass spec to analyze the VOC composition and concentration of the air we have collected. And the analysis is based on EPA method, and we basically can analyze for the VOC compounds with boiling point from 35 degrees C to 250 degrees C. And we have a target list of VOCs of over 130 compounds. And in the middle figure, I'm showing the aldehyde sampling. So we collect aldehyde onto our DNPH tubes, shown in this yellow plastic tube, and we analyze aldehydes according to EPA method using HPLC. And we have a target list of 15 aldehydes. And both the analytical techniques have a detection limit of 0.2 microgram per cubic meter, and the limit of quantification is 0.5 microgram per cubic meter. In addition to the integrated offline analysis, we also have a portable device, the FTIR, is used to screening for the chemicals on site. And this FTIR instrument has a target list of 50 compounds, and it also have a untargeted library of over 300 compounds. And on next slide, the other air pollutants we are interested in is particulate matter, or PM. And PM is a mixture of solid particles or liquid droplets that's suspended in the air. And the inhalation of PM in the air may be associated with pulmonary or cardiovascular diseases. So in our field study, we brought in our online particle measurement instruments. The left one is the scanning mobility particle sizer. It can measure particles from 10 nanometer to about over 400 nanometer in real time. And the second is optical particle sizer. It can measure the particles from 0.3 to 10 micrometer in real time. And the third picture shows a 37 milliliter cassette and filters that we use to collect the airborne particles. And with that, we can measure the gravimetric measurement, and we can further extract the particles and use our SAP mass spec to analyze the metal compositions of the collected particles. And next slide. So in our field study, the objective is to understand the impact of resin 3D printing on indoor air quality. And we also picked, because it's in the dental school, we also pick another activity that is routinely happening in the dental school, which is milling or grinding activity. So we select 3 monitoring sites in each dental school. So we have the 3D printing room or 3D printing area that has the resin 3D printers and also the post-print processing unit like the alcohol bath and also the cure units. And also you can advance. Yeah, and the next one. Yes, so here are the pictures. The left picture showing the sampling next to our 3D printing units. And the second monitoring site is the focus on the milling or the grinding activity. And this area has no resin printers and only the milling or grinding machines or the tools, which is shown in the middle picture. And to look at the impact, we also compare our measurement to a control area where we don't have 3D printing or milling or grinding activities, just as a baseline. And for each could you go back? And for each monitoring site, we are measuring PM and VOCs. The VOC sampling target for 1 hour. And next slide. Now let's get into some results. So this slide is showing the particle size distribution in the in one dental school. And on the figure, the left figure is showing the particle number distribution, and on the right is showing the particle mass distribution. The blue line indicates the sampling taken in the printing area, and the orange line indicates sampling taken in the milling area. So from the left figure, we can see the majority of the particle numbers are in nanometer size. So we can see on the peaks of this distribution are about 100 nanometers or less. And both the 3D printing and the milling area showed smaller particles, and they are mainly ultrafine, which is less than 100 nanometer. And we know that because these ultrafine particles are so small, they are highly mobile and they can penetrate deep into our lungs. But when we look at the right figure, we can see from the milling area, there is a big increase of particle mass in the micrometer size particles. And the next slide is the particle size distribution of the second school. We can see the similar pattern of the particle distribution. Also from the left figure, we see normally ultrafine or up to like 300 nanometer particles in the number distribution. And on the right figure, we can see for the mass distribution, we have a peak on the micrometer size particles. And the next slide I'm showing a summary of the particle concentration grouped by different school. And we can see that the 3D printing lab has relatively lower particle number and mass concentration compared to the milling or grinding area. Chrissy also mentioned that our chamber lab characterization also showed resin 3D printer is emits minimal particles, and this makes sense in our field measurement that milling activity is more of a source of particles, and especially when we look at the PM10, that is 10 micrometer or less particles, that milling lab has a much higher concentration of PM10. And the next slide is showing the particle metal composition. This is only done in one dental school, and we have the metal composition analysis on 3 samples. We use the outdoor sample as our baseline, and we have the samples taken from the 3D printing area and also the grinding area, and compared to our baseline, we can see that the grinding area showed an increase in lithium and chromium, and the printing area showed an increase in zinc. But all of these metal concentrations are below the occupational regulation levels. And next slide, let's look at the VOC results. So these 2 figures showing the total VOC concentration in the 2 dental schools. Our total VOC indicates a sum of the compounds from C6 to C16 toluene equivalent concentration. So this TVOC analysis doesn't include the very volatile compounds. And from the 2 figures, we can see the 3D printing area or the 3D printing lab with the resins, with the resin and also the post-process units always has higher TVOC concentrations than the milling and the grinding area. But we can also see here on the left, the hallway TVOC concentration may be even higher than the printing area. That could be because the penetration from the 3D print lab to the hallway, that could be the difference in the ventilation rate. And for the total VOC concentration levels, the lead criteria has a benchmark total VOC concentration of 500 microgram per cubic meter for the green buildings, and the hallway total VOC concentration on the left figure is reaching up to that criteria. And also from the right figure, we can see that outdoor total VOC is generally lower than the indoor concentrations. And the next slide. Let's get into the individual VOC compounds. So here on the table, I'm showing the top 10 most detected VOCs in the 3D printing lab. We can see there are some unique VOCs only detected in the 3D printing area, not in the milling room or the highway, and also the compounds with the highest concentration shown on the 3D printing column. They could be associated with the 3D printing process and also the resin and the reagents that being used in the 3D printing process. And generally, the VOC levels in the milling room is relatively low because we don't expect a source of VOCs in the milling room. And also we have detected several chemicals of concern that may be hazardous to the human being. And overall, in this dental school settings, we have found 1 exceedance of the compounds comparing to the regulation limits for indoor air quality, which is formaldehyde. The limit is 9 microgram per cubic meter. It could be high in the 3D printing area or in the hallway. And next slide shows this summary individual VOC concentration for the second dental school. And also we can see that the 3D printing room has higher VOC concentrations compared to the other area, but there is the most abundantly detected compound is isopropanol, which is the alcohol that has been used for the wash activity after the part is printed with the resin. And we can see that the grinding area also has a higher concentration of isopropanol, which could be the chemical compound being diffused into the different area. And we also detect some chemicals of concern, and some of them share the same compounds between the two dental schools. And in this dental school, we didn't see any exceedance of the VOC levels compared to the indoor reference levels. And next slide. So the portable FTIR, we use this instrument as a screening tool because the FTIR has a much higher detect limit based on the 62 VOC compounds that has been detected from our analytical lab. 37 of them are on the FTIR target list, and 21 of them have been detected with both LOD. So we use this instrument to see the trend and the peaks of the VOC compounds at our site. And on the right figure, we have validated that FTIR it may not be the best tool for the low concentration site, but it can show you the trend. For example, on the right figure, the FTIR can identify the highest concentration at the best area of isopropanol, and the isopropanol concentration in the other area are relatively lower. So we can use this as a tool for screening of the VOC concentrations. And then next, I will hand over to Mark to summarize.
Thank you very much, Chen. So to summarize the results presented associated with both field and chamber studies, I want to begin with particulate matter and point out that ultrafines are the predominant species that are present within the aerosol size distributions in the 3D printing areas. There are peaks of both ultrafine nanometer size particles and micron size particles that are present in the milling and grinding areas. So there's a very different aerosol size distribution profile associated with these two different activities. It's also important to note that typical optical particle scanning devices like indoor air quality optical monitoring devices that are available at reasonably low cost don't do a very good job of monitoring for nanoscale particles. So that's something to consider if you are placing sensors to evaluate indoor air quality, is to ensure that the sensor is appropriate to deal with the hazards that may or may not be present. So as noted, the grinding and milling room showed higher levels of particles in general than the 3D printing room. And if you look at the mass distributions, the grinding and milling area had a lot higher levels. And that is because they had a significant number of larger particles, which just weigh more than very, very small particles. Compared to the grinding areas, the 3D printing areas typically showed lower particle concentrations, but higher particle numbers. It's interesting to think about how we evaluate particulate matter in indoor air quality Do we want to use occupational health regulations, which typically are in the milligram per cubic meter type of range, or do we want to use more conservative metrics like national ambient air quality standards, which are designed for evaluating outdoor air? So for our studies, we used the national ambient air quality standards because they were a couple of orders of magnitude lower than OSHA PELs for particulate matter. It is important to note, though, even the national ambient air quality standards are focused on micron-sized particulate, and even though PM 2.5 is technically defined as PM that is 2.5 microns and smaller, using a mass-based readout for very, very small particles can be somewhat problematic because the very small particles don't typically weigh all that much. Next slide, please. For VOCs, one of the standouts that we saw in both chamber and field studies was formaldehyde. And formaldehyde was the only VOC that was detected in the field studies that had an exceedance of threshold criteria. So the Venn diagram on this slide shows that when we do chamber-based studies where we have very low backgrounds in the air and can attribute most of the things that are detected specifically to 3D printing operations, that we are able to detect 88 individual VOCs. Among those 88, 12 of them were detected in both field studies. So that is indicative that those 12 are highly associated with 3D printing processes that are representative of probably dental schools in general. Those 12 common detected VOCs are presented in the table on the right of the slide. It's important to note that a few of these are known or suspected carcinogens, and that there are various stages associated with interacting with 3D printing operations, whether it is curing or washing or printing or all the way across the spectrum of all of those operations. There are some chemicals that are unique to specific phases and other chemicals that are present throughout the entire process. Next slide, please. So we did see pretty good consistency in both particle size distribution related to particle number and particle mass, looking at 3D printing areas versus milling and grinding areas across both schools that were evaluated. And we have to keep in mind that there are very unique characteristics associated with each site that make comparing site 1 to site 2 difficult in terms of an apples to apples type of comparison. So there are differences in environmental conditions just associated with HVAC operation, maybe the time of year when the samples are collected, ventilation conditions and room geometry that are unique to the individual locations, and also the types of printers, the types of printing materials, and the number of printers that is being used in individual or in combination during the time that the samples were collected. So next slide, please. So some of the things that that we were able to learn in hindsight associated with conducting both these chamber and field studies is that when you're developing a sampling strategy, that it's really pretty critical to have an idea of what kind of hazards you are expecting to see in advance and where their potential sources may be. And this may be from review of safety data sheets or chemical inventories, but this gives you a good jumping off point to establish what types of sampling media and devices you're going to employ in order to capture things that you think are likely going to be present. And that you always need to have a control location for comparative purposes, and that control location can be a room that does not have the operations that you're evaluating present in, or it can also be outdoor air. Ideally, it is good to collect outdoor air and have a control location that has no 3D printing inside the building, and have evaluations of 3D printing operation rooms for comparative purposes. Sometimes that's not practical though. And sampling and monitoring duration, you have to be cognizant of the limit of detection for your analytical techniques. So you need to make sure that samples are collected for a long enough period of time that you will be over your analytical limit of detection and able to detect and report a reliable value. And that activities during sampling duration need to be controlled, and they need to be recorded. So you can identify any kind of time activity relationships that are associated with peaks or valleys in the exposure profile. So qualitative instruments like the FTIR are really good for providing this kind of information, as is the real-time instrumentation that does particle detections. Sampling locations and monitoring sites have unique attributes associated with them, and that all of the VOCs or particle emissions that are detected may be emitted from sources that are not 3D printers. So it's important to keep that in mind as well, and that if possible to empirically measure ventilation rates or air mixing rates. That is ideal, but again, oftentimes not practical. Typically, you can get this kind of information from building engineers who have information related to balancing of the ventilation system. And that's an important criteria when evaluating the acceptability of ventilation conditions at a given site. And that we also have to remember that emissions are not always associated with the things that we're studying. They can be from occupants or activities. So this can be things like fragrances, or if people happen to be smokers, they often emit particles as well as VOCs. And that sometimes your analytical instrumentation can be a source of confounding in your studies. So it's important to understand what types of emissions can be associated with analytical instrumentation as well. So for instance, we were really interested in looking at isopropyl alcohol as it's a solvent used in the wash step, but it is also the condensation fluid that our nanoscan uses. So our particle measurement instrument was actually a contributor to isopropanol levels, which we had to work out after determining that that had occurred. Next slide, please. So we want to open the floor for discussion if there are questions.
There's still one question in the chat. Of waste treatment and require a waste treatment permit. Isn't drying waste treatment and require a waste treatment permit? This was TAMU when they were talking about that they're looking to solidify their resin for waste disposal.
So we haven't had any requirements for that yet. Basically, we're just still doing the procedure, dry it out, and just dispose of it as solid waste. So from what we've seen, it appears that once you dry it out and dispose of it, that way it doesn't contribute to like any hazardous waste anymore, pretty much. At least that's what our researchers have found, and that's the procedure we're following currently.
The Q&A is currently has no questions. We just had a question. Would you be able to share the application settings for the data collection via the GasMet FTIR?
Are you looking for the time intervals or?
That might be
So
helpful.
basically, we also collect the tube samples, and we have the results from our analytical lab, and that is our target list for the FTIR analysis. And we use that to screen over what the FTIR can analyze, and we select those compounds that are both on our list from analytical chem lab and also on the FTIR target list. And we use the software come with the FTIR to do the analysis and report the concentration.
Someone's asking about a copy of the slide. I do know the recording is supposed to be available on the cafe by tomorrow, but I'm not sure of the actual slide deck. And someone is asking, what was the continuous monitoring app?
Yes, so I'd be happy if you want to email me. I'd be happy to give you that information. I don't want to be out endorsing this tool. I really want to encourage people to do their own research on tools like this. Mark did a really good job of trying to explain that there's limitations on these devices, right? These are not high-level sampling tools. I'm using this to give sort of awareness and recognition that we have a direct reading opportunity to see, hey, when we're running this equipment, we're getting readings, right? Now, how quantitative are those readings? We really can't say, but it's a red flag, or it's giving us a warning signal. So please feel free to email me. I'll make sure if you all can find me on Shima Connect very easily. I'm not hard to find. Look at the NSU website, you'll find me. I'd be happy to give you information on what we're using, but I really would love you to do your own research as well. I'm not endorsing this, CIRI is not endorsing it. But what has been beneficial for me was, we try to convey to the end users concern. And I think when they saw a picture and they got this information, they recognized, hey, I need to pay attention to this. There is definitely something happening here that may impact my health. And if I could say that that's really the whole purpose of this presentation. This is why we did this at the annual conference. It's why we're doing it today. You don't have to, do your own sampling, right? But you're now informed. You now have an idea that this equipment does have hazards associated with it. Ventilation, depending on your unique space, is going to have a different impact on what that looks like on your campus and your spaces where you have 3D printers, especially resin 3D printers. So hopefully, good awareness for all of you.
All right. I'm going to thank you all for coming and our amazing group of speakers. We are at over 2 p.m. or Eastern and 1 p.m. Central. I think everyone's pretty open to carry this conversation after the fact. Don't forget you can use the Shima Cafe to reach out to Beth. And if you have any questions, please reach out. But thank you, everyone.
Hey, Elizabeth, I just
Yes.
wanted to say that we have the full reports on both of these studies on the CIRI website. If you'd like to check out chemicalinsights.org, and if you want to read the full study reports, they're there. So sorry, yeah.
Yeah.
Excellent.
All right.
Thank you very much.
Hey, thank you for having us. Bye.